Hello, everyone, and welcome back from the break. We move now to our second keynote of this session, which will address computable medical knowledge research in China. And we are delighted to have as our keynote speakers, Dr. Luxia Zhang and Guilan. Let me introduce them both before we see and take advantage of their presentation. Dr. Zhang is professor in the renal division of Peking University First Hospital and associate dean at the National Institute of Health Data Science at Peking University. She obtained her MD degree at Peking University and followed that with an MPH degree at the Harvard School of Public Health. For the last 17 years, her research has focused on prevalence, risk factors, intervention, and management of kidney disease in China. Most of her work provides firsthand information about kidney disease in China and has gained wide attention internationally. More recently, during the last 7 years, she has initiated several projects based on big data and using machine learning in the field of major non-communicable chronic diseases. Her studies have been published in several prominent medical journals, including the New England Journal of Medicine, Lancet, and the BMJ. She's vice president of the Committee on Health Data Science and Digital Medicine in the China International Exchange and Promotion Association for Medicine and Healthcare, and she's vice president of the Beijing Young Nephrologists Society and a member of the Lancet Digital Health International Advisory Board and the editorial boards of several other prominent journals. Dr. Guilan is Associate Research Professor at the National Institute of Health Data Science at Peking University. She received her PhD in Decision and System Science from the University of Manchester and a Master's in Engineering and Bachelor's in Engineering from the National University of Defense Technology in China. Dr. Kang's research focuses on clinical decision support systems, medical data mining, multiple criteria medical quality evaluation, and learning health systems. She's been funded by the National Natural Science Foundation of China, the Ministry of Education in China, Beijing Municipal Science and Technology Commission, Peking University, and by the Michigan Medicine Peking University Joint Institute. She's a standing committee member of the Application and Management of Big Data and Health Committee associated with the Chinese Hospital Association and a standing committee member of the Data Analysis Branch of the Chinese Association of Geriatric Research. So we will now see their talk on computable medical knowledge research in China.
Good morning, good afternoon, and good evening, distinguished guests, ladies and gentlemen. It's really an honor to have the opportunity to talk at the MCBK Global Meeting 2022. I'm Luxia Zhang from the National Institute of Health Data Science at Peking University, also a nephrologist from Peking University First Hospital. My joint speaker is my colleague, Dr. Guilan, who has been devoted to promote the concept and have conducted studies of computable biomedical knowledge in China. Today, we would like to share our experience of studies focusing on computable biomedical knowledge in China. We have no actual or potential conflicts of interest in relation to this presentation. So for today's talk, firstly, we will briefly introduce the background of CBK, which you might be familiar with. And we will introduce our studies regarding CBK, especially the practice in the field of kidney disease in China. Finally, we will talk about our next step. So the first part. In 2006, the Institute of Medicine, which is currently the National Academy of Medicine of United States, offered the first working definition of learning health system. Professor Friedman the MCBK community chair used a directed and closed loop, including data, knowledge, and practice to illustrate the continuous and the cyclical learning process in a learning health system. In this learning cycle, data can be captured from medical practice through information systems. New knowledge can be discovered from data using a variety of analytical methods. The knowledge-based or model-based decision support systems can be developed. And finally, the decision support system can be integrated into daily workflow to improve the efficiency and accuracy of healthcare. For simplicity, D2K, K2P, and P2D were used to describe the K process in this learning cycle. In the context of learning health system, computable biomedical knowledge plays an imperative role in speeding up the K2P process. And the CBK research includes the first one, how to make narrative knowledge and tested knowledge contained in data computable. The second one is how to make computable knowledge findable, accessible, interoperable, and usable. And finally, how to develop computerized tools to support intelligent medical decision-making. Here are two examples of CBK tools that have been developed by domain experts. The first one is called Open Clinical Platform. It's developed by Professor Zhang and his team at Oxford University. It aims to transform human-readable narrative clinical guidelines to computer-executable and actionable guidelines. The other CBK management tool I put in this slide is Knowledge Grid Platform, developed by Professor Friedman and his team at the University of Michigan. It helps to package both narrative clinical guidelines and executable models to computable knowledge objects, and then provides API for external applications to trigger these knowledge objects in a real-time way. The Agency for Healthcare Research and Quality, AHHQ of the United States, use 4 levels of knowledge to summarize the current knowledge related products and service. And these 4 layers include narrative, semi-structured, structured, and executable knowledge. In the era of big data, we can see that information technologies and computing science can help transform traditional narrative knowledge to structured and executable knowledge. And it's a type of knowledge evolution process. So next, for the following slides, I will introduce what we have done about CBK research in China from narrative, structures, and computable knowledge perspective, respectively. As to CBK research in China, first of all, by the collaboration with Professor Friedman's team, we have been conducting a learning health system study in China. As I have mentioned previously, I'm also a nephrologist at Peking University First Hospital, and therefore we choose chronic kidney disease, CKD, as the target disease area for the LHS study. Globally, CKD is a highly prevalent condition with a prevalence between 10 to 15% and has a trend to continuously increase. In China, the prevalence of CKD was 10.8%, and the number of patients with CKD was estimated to be about 120 million. Meanwhile, the awareness rate of CKD was only 10%. The capacity and quality of kidney care varied substantially in China, so clearly there are space for improvement. We planned to implement a regional and national learning health system in which the D2K, K2P, and P2D process could be sped up for CKD management in China. The narrative knowledge source of this learning health system study, including KDIGO clinical guidelines, which is a globally acknowledged series of guidelines for CKD diagnosis, treatment, and management, together with the published literature in the field of nephrology. The data source used for this study includes the regional health information system running in Yingzhou district of Zhejiang province and the China Kidney Disease Network, CKNet, which was built by our team at Peking University. For the rest of my talk, I'll use CKD as an example disease and briefly introduce what we have done to discover new medical knowledge and make them computable and shareable for intelligent clinical decision support in CKD management practice. Medical big data provide the foundation of different clinical risk stratification or prognosis prediction models. One of our data sources is electronic health records from the Yingzhou district of Ningbo City, which locates in a relatively well-developed area in southeast China with a population of 1 million. Under the national strategy of promoting the application of medical big data in China, a number of local governments in developed areas have put a lot of efforts into building EHR data warehouse, and then collaborate with relevant commercial companies and the research institute for data mining. As for Yingzhou, data from local hospitals, public health service, administrative and claims database are collected and integrated at one big data platform. After de-identification and data cleaning, data are used for administrative purpose, as well as providing data service to a variety of stakeholders. Another data source is focused on kidney disease. CKNet is an academic initiative led by the Peking University, which is the first of its kind in China. The mission of CKNet is to integrate various sources of data involving kidney disease in China, as well as using cutting-edge technology to provide data-based evidence for policymaking, to strengthen academic research, and to promote effective disease management in the field of nephrology. Under the permission of relevant authorities or data owners, CKNet has access to a variety of types of databases, including administrative data, EHR data, data from public health platform, epidemiological studies, and claims data. The data resources are still expanding, and we are planning to include more dimensions of data regarding social determinants for kidney disease. The data are managed by the big data platform of our institute with high standard of security. So based on the framework of CKNet, our team has produced research findings about the spectrum of CKD in China. CKD is an entity of disease due to a variety of causes, and understanding the composition of causes is important to develop proper management strategy. For the long term, nephrologists used to believe that in China, glomerulonephritis is a major cause of CKD. Based on an administrative data set of 35 million hospitalized patients, we find that starting from 2011, diabetic kidney disease has exceeded glomerulonephritis and became the #1 cause of CKD. You can see the trend is even more obvious in 2015. Our study highlights that after the failure to control the epidemic of diabetes, we cannot afford another failure to mitigate the epidemic of diabetic target organ damage, including CKD in China. Campaigns to control the increasing burden of diabetic kidney disease are needed in China. So along that line, we have initiated the process of producing an expert consensus on the diagnosis and treatment of diabetic kidney disease in order to improve the quality and the consistency of the healthcare. In the consensus, risk factors and the diagnosis of DKD were described. Guidelines of the management of blood pressure, blood glucose, and other cardiovascular risk factors were listed, and the condition for transferring the patients to nephrologists have also been discussed. Also, we have generated and delivered annual data report based on the framework of CKNet, which comprehensively presents general and medical characteristics, medical care service, and healthcare resource utilization of patients with kidney disease in China. The majority of the information has not been reported previously in China, and may be the first example of its kind in developing countries. Our first annual data report was published in AJKD, primarily focused on pre-dialysis CKD patients. The second version of ADR was published in Kidney International and was expanded to dialysis patients since 2 national claims databases were included. In 2020, our third ADR was published in KI with detailed information of dialysis patients in 3 provinces, as well as dialysis patients aged younger than 18 years. We also have the Chinese version of ADRs. So for the following presentation, Dr. Kong will continue to talk about structured knowledge. Dr. Kong, please.
Thank you, Luxia. I'll continue to introduce our work. In addition to generating narrative knowledge from CKNet data, as Luxia just introduced, we have also done a job for transforming international authoritative clinical guidelines to structured and computable knowledge to aid clinical decision-making. In CKD management, according to the KDIGO 2012 clinical guideline for the evaluation and management of CKD, our team used traditional if-then rules to formalize the logic contained in the guideline and constructed if-then rule base. The rules listed in this slide are the rules for diagnosis of CKD and anemia, and making judgment about whether a patient with CKD and anemia has ESA hyporesponsiveness. We then used computer programs to store the rule base in computers and make the knowledge readable and understandable for computers. Also, we have done another job of transforming published clinical literature to structured knowledge. We have been doing research about using text mining tools to extract subject, predicate, object, SPO triples from the literature so as to construct knowledge graph for various disease diagnosis and treatment. It is worth mentioning here that there may be some controversial, conflicting, and contradicting sentences in the published literature, since the results of a clinical study are usually generated in a certain experimental or observational condition. The conclusions drawn from this study may not be 100% true under other conditions. Therefore, a SPO triple should be extracted together with its context and clinical conditions. Here, the context and clinical conditions lead to uncertainties. Our team proposes to classify the uncertainties into contradicting and conditionally dependent types, and to employ new methods to extract an XPO triple together with its uncertainties, and thus to build a dynamic knowledge graph with uncertainty representation. At the moment, the construction of a knowledge graph for CKD management is underway. In parallel to making narrative knowledge structured and computable, another important research direction in CBK is to derive computable models from big data based on the EHR data extracted from the regional health information system in Yingzhou. Our team has developed a computing phenotype for CKD identification. In development and test of the data-driven phenotype tool, we used ICD codes and physicians' diagnosis reports in combination to identify CKD patients. Patients' lab test results, such as eGFR and some urine test items, were used as independent variables to do computing. If a patient's lab test results have been abnormal twice in 3 months or longer, the patient is defined as CKD. If a patient's lab test results have been abnormal once, or the abnormal condition has lasted less than 3 months, the patient is considered as with CKD risk. This computing phenotype has been tested by the EHR data in Yingzhou, and it works well. In addition to developing computing phenotypes, our team has been using advanced machine learning methods to develop risk stratification and outcome prediction models for CKD management. Based on the real-world EHR data in Yingzhou, we have done a lot of data cleaning and pre-processing job, and we have built a specific CKD database in Yingzhou. It is based on the CKD database. Our team has tried to develop kinds of risk prediction models that can assist clinical decision-making. At the moment, the development of a random survival or forest-based model for predicting fracture risk of CKD patients, and an ensemble learning-based model for predicting the risk of developing CKD among diabetes are underway. Moreover, our team has developed a localized CBK management platform with a strong support from Professor Friedman and his team. We developed a localized knowledge grade platform for managing computable knowledge objects. At present, only computable knowledge for management of a few chronic diseases, such as CKD and diabetes, have been covered by the platform. The if-then rule base mentioned in one of my previous slides and a CKD, a risk scoring model, have been packaged as computable knowledge objects in the platform. The screenshot displayed on the right side of this slide is the interface for physicians to input data of a CKD patient with anemia before a treatment recommendation can be generated. And the domain knowledge behind this treatment recommendation are the if there rules extracted from the KDIGO guideline. This is the scenario for application of the knowledge grid platform in clinical practice. We can see that when a CKD patient comes in, his or her data will be inputted in the EMR system and then to a clinical data repository. Since the knowledge grid platform provides online CBK services for all system users, nephrologists can use the online CBK tool to support their clinical decision-making. We have now established a strong research partnership with the Center for Disease Control and Prevention, CDC, in Yingzhou. The CDC in Yingzhou and the CKD Academic Association there will help us promote the application of knowledge grid tool in their daily clinical practice. We believe that a knowledge grid platform will be used by general physicians in local communities in Yingzhou in the near future. Opportunities and challenges. First, opportunities. There is substantial variation of healthcare quality in China. Clinical decision support systems empowered by CBK are strongly needed. Meanwhile, huge amount of data in medicine and increasing number of publications are being accumulated. There is ample space for CBK research in China. Opportunities bring challenges. CBK is a new concept in China, and it needs to be promoted and accepted by medical society and stakeholders. At the same time, the technical and medical advances need to be integrated into CBK research and application. At last, there are still some technical, administrative, and ethical issues waiting to be addressed for integrating CBK-empowered clinical decision support tools into practice. Our next step, driven by the opportunities and challenges brought by CBK, our team has made an overall plan for CBK research and promotion in China. We propose a CBK ecosystem concept and a framework. We think that CBK ecosystem is a cyclical system with continuous improvement capability for CBK development and application. It consists of three core processes: CBK generation, CBK dissemination, and CBK application, where the CBK engineers are responsible for generating CBK from published literature or real-world big data. The CBK providers are in charge of disseminating CBK to the right population at the right time for right purpose. And the CBK users are the consumers of CBK, and they use CBK-empowered tools to support their decision-making, and their daily practice would in turn help generate new data for another round of CBK development. In CBK generation phase, we hope to generate methodological innovations in the area of transforming narrative knowledge to CBK. We plan to propose innovative and pragmatic text mining techniques in the field of deriving CBK from real-world big data. We plan to develop advanced and robust data mining methods. Here, text mining research areas include ontology, building, information retrieval, and so on. Traditional data mining methods may include association rule mining, clustering analysis, deep learning, and etc. And we'll try to develop, assemble, or optimize learning models with better classification or prediction performance. And in CBK dissemination phase, we propose to build a CBK repository that can be used to store, audit, and disseminate CBK. And the repository should meet the ethical, technical, and operational requirements in practice. Further, a CBK dissemination strategy is developed. First of all, we should do the job of identifying the target CBK audience who needs to be informed at awareness, understanding, and action levels. And then we need to identify possible disseminating channels, including academic journals, conferences, and seminars, internet websites, or collaboration networks. Finally, as long as the disseminating channels have been determined, the developed CBK can be disseminated through journal publications, conference talks, and online services, and so on. And the ultimate purpose of CBK dissemination is to facilitate its use in practice. The final phase of CBK ecosystem is CBK application, as there are too many branches of biomedicine. Here we select only two typical scenarios in biomedicine to illustrate the potential CBK application. This is in the context of learning health system. For the CBK generated from narrative literature or real-world big data, we can store or package them into a CBK repository, which is similar to the knowledge grid platform that we have developed, and then try to integrate the CBK tool into daily clinical workflow to support physicians' clinical decision-making. Here, the CBK-empowered decision support tools can be implemented as online services or mobile apps. And in the context of AI-driven drug discovery, we plan to use innovative and advanced artificial intelligence techniques and methods to derive various data models from target data, drug data, and some other data sets. And then we'll package these models as standardized CBK artifacts in a CBK repository, and finally apply the CBK empowered tools for target prediction and new drug discovery and some other applications in AIDD. Furthermore, we'll continue the research and implementation of LHS in China. Meanwhile, we plan to unite peer experts to form an MCBK community in China to promote CBK persistently. At last, acknowledgements. We greatly appreciate the strong support from the National Health Commission and the Ministry of Science and Technology of China, Peking University, Advanced Institute of Information Technology at Peking University, China Standard Medical Information Research Center, member volunteers and participants contributed to the CKNet. And the last but not least, Professor Charles Friedman's team at the University of Michigan. Thank you very much for your attention.
Well, very, very nice. Thank you, Guilan. and Luxia for this excellent presentation. We move now into our question and answer phase, and we're delighted to have you here in person. And I'll begin with a question. I couldn't help but notice your mention of ethical issues that relate to use of computable biomedical knowledge. And of course, ethical issues are of great interest to us and really around the world. I wonder if you could expand on the ethical issues that you see to be prominent in China as you deploy your learning health system and CBK.
Yeah. Okay. So that's actually a very important question, and I would like to address first. Maybe Guilan will talk from her point of view. I think from the ethical point of view, it's quite the most relevant scenario is clinical decision support, maybe empowered by artificial intelligence. Because in China, there is a lot of debate regarding that issue, such as who is responsible for clinical decision support empowered by artificial intelligence, whether it's a company who produce the product or the physicians should be responsible for that. And also there are some controversy regarding the AI algorithm in such kind of point of view. We talk about, such as in US, there might be some discrimination regarding certain races because of the data generating the algorithm. Also, there are such kind of debate in China. So I think it's quite an important issue here.
Yes, and Luxia has said the actual situation of ethical issues in clinical decision support in China, actually from the data generation, the data regulation rules are very strict in China. So from the data to generating the models, there are some very important ethical issues. So there are both ethical issues in data and models and the final system application in practice. So we need a lot to address in the future about the application of learning health system in China. Yes.
Thank you. Thank you very much. We'll turn now to some of the questions that have been contributed by our participants in the meeting. And this first question takes us into a little more technical domain, and this is a question about your CKD if-then rules that you described, and a question about how they are expressed. Are they expressed in a formal expression language, or are they expressed in pseudocode?
Okay, I'll explain the if-then rules in our platform. Actually, our if-then rules are extracted from the critical guideline for CKD diagnosis and management. And we only use a key part of the CKD diagnosis rules. And we use if-then rules in natural language first. And then we invite our engineers to use computing language to code the natural language if-then rules, and then use some programming algorithm to trigger the rules when the patient's data are input into the platform. So it's a knowledge-based inference mechanism implemented in the platform. So that's the explanation about the if-then rules.
Okay, thank you. Thank you. That was very helpful. I wanted to ask you also about in relation to the very important and ambitious plans you have for CBK and learning health systems in China, whether there is an educational infrastructure in place to train the next generation of, or even a current generation of workforce to support not only the research and development, but also the implementation aspects of what you plan to do.
Yeah, in our institute, we have several educational programs targeting at both, students at the university and also physicians and relevant expertise. So we are planning to include the concept and the idea of CBK in such kind of education program. And, your help is more than welcomed during the process. Thank you.
Okay, thank you, Luxia. Another question from our participants, and this goes to your knowledge graph. And the specific question is, how does your knowledge graph interact with data from an EHR, and could it work with FHIR data?
Okay, I'll answer the question. Thank you very much for this good question. Actually, our knowledge graph about CKD management is ongoing, and we have not yet implemented the knowledge graph in practice. And the link between the knowledge graph and the EHR data is still needed us to implement. So maybe in the near future, in September or November, we can report our progress about this work. Thank you.
Mm-hmm. Thank you. Another question from our participants. This goes to the Chinese health IT industry, and the specific question is about your interactions and your level of engagement of this exciting work with the health IT industry in China. And are they interested in your approach? And are they interested in the standards-based approach you plan to take?
Yes, definitely. We have building the collaborative relationship with some health IT companies, and they are starting to thinking in this way. So they are very interested in such kind of work, and they think such kind of research could help to improve their products. So the answer is yes.
Okay, very good. And one last question. You spoke about social determinants of health, and I'm sure you've looked at the extensive literature globally on social determinants of health around the world. And I think a lot of us are curious about in China, whether you've seen significant differences in the social determinants of health between China and perhaps other nations of the world, or is it pretty much the same set of social determinants in China that are seen elsewhere?
Yeah, I would say regarding the social determinants, the majority of the study are focusing on environmental factors, and the observed association are quite similar with the other part of the world. Yeah, but there are some characteristics of China, but the association are largely the same, but with slightly different extent.
Thank you. Okay, well, this brings us to the end of our time for this question and answer session. Luxia, Guilan, we can't thank you enough for your presentation and for the excellent responses that you gave to the questions.